All right, as I was mentioning in the last video, we use sound waves, which are seismic waves. Seismic waves, the reason we started using seismic waves is, you know, almost, it's got almost 100 years now. We were able to detect these. These occur naturally, of course, during earthquakes. And humans started studying these sound waves, and we were able to make a picture using sound. It's the same thing that happens. When I have two boys, they're both adults now, but before they were born, I can remember getting their ultrasounds. You know, it's, and we used set. The doctors use sound to be able to take pictures. All right. So anyhow, let's move on. All right. So this is an example. It can't be like any sound. The sound has to come. It has to be a pretty substantial sound to actually travel through the earth. All right. So now when earthquakes occur, there's actually two types of waves, right, that occur, and we'll discuss these in a little bit more depth here. They're called S waves and P waves. It actually stands for primary waves and secondary waves. But the way I always remember it in terms of astronomy, what's important to astronomy is that S waves can only go through solids. All right, so they're both generated, right? Let's say an earthquake occurs. Okay, so now, since we've been studying sound waves, earthquake waves for over 100. Well, I think it's been 100 years. It's really close to being 100 years, at any rate. We now, of course, have detectors all over the planet. All right, so let's say there's an earthquake, right here, and the S and the P waves travel outward as they do, and as long as they're between where the earthquake occurs and where the detector is, as long as there's just solid rock between the two, the detector will record both S and P waves. All right. So notice as you get over here, just think about the curvature of the Earth. You get over here, and well, actually, over here it's actually much more complicated. Let me just go on the other side of the Earth. Right, on the other side of the Earth, because the S waves have traveled through liquid. And in fact, that's how we learn that there's a liquid core inside of the Earth. P waves can travel right through the liquid core, but S waves cannot. And so if you're on the opposite side of the Earth, you can still detect the P waves, but you get no S waves. There are certain zones. It's actually a much more complicated picture than this, where basically the waves cancel out, and so there's regions on the Earth where there's no waves detected at all. They're not this big. They're just using this as a demonstration. At any rate, we know about those. Like I said, this has been studied for a long time, and from this, from the picture that we get. I mean, this is not a single earthquake occurring, and you instantly get this picture, right? This is hundreds and hundreds of thousands of earthquakes that have been occurring, and we've been recording them. But by the way, we actually sent a spacecraft. It was called the InSight spacecraft to Mars to look for little Mars quakes. It's no longer operational, but for a long time we were actually measuring some earthquakes not earthquakes, I guess they'd be called Mars quakes on Mars. And of course we did this with the moon when the astronauts went to the moon. But anyway, here, let's go further into this. So you have the actually, let me mention something else here. You might notice, of course, there's a liquid core. It's mostly liquid. It's liquid iron and nickel, and then there's a solid core. So you might say, well, how do we even know that there's a solid core in here? Just like when light passes through a lens, the light bends, right? I mean, we're all aware of that. Or light passes through water. Light is a wave. Light can be thought of as a wave, actually, and it'll bend a certain way, and so do these sound waves, right? The sound waves bend, and the amount that they bend tells us what the size of the solid core is, and of course, from where you don't see any more waves, you can tell what the size of the outer liquid core is as well. All right, let's keep going. So as I said before, there's primary waves. That's what the P waves are called, and then there's secondary waves. All right. So remember, the S waves can only travel through solid material, and so the S waves, okay. So there's two types. These are also known as the P waves. Okay, that's this first one. That's this A right here. So these are also in physics we call them longitudinal waves. That is, the thing that's waving is in the same direction that the wave is traveling. Okay, so that's it's like if you had a spring and you pulled the spring, and the compression wave moves along the spring. All right, and then there are what are called transverse waves. That's actually what the S waves are. The S waves are this B column right here. And so transverse just means that the wave, it's waving perpendicular. So it's waving back and forth perpendicular to the direction the wave is traveling. So the wave might be traveling, down the page here, or down the slide that I'm looking at, that you're looking at. But what's the wave is actually perpendicular to that. And so that's called a transverse wave. And so because the transverse wave works by it basically, if it hits rock, the wave goes out and then comes back in, goes out, comes in, goes out, comes in, right? If it hits liquid, liquid is such that it doesn't push the wave back. So that's why you don't get, S waves cannot travel through the liquid core, the outer liquid core. All right, so that's a little bit about S waves and P waves. All right, so observations show that P waves, this is like, P waves can go all the way through the Earth, and S waves don't, right? So the Earth does have a liquid core, and not only that, like I said before, we can actually measure this. We know the size of it very, very accurately, and we can measure the size of the liquid core. I'm sorry, the size of the solid core as well. Right. So there's an outer liquid core, but by the way, the outer liquid core is where the magnetic field is generated. The magnetic field of the Earth, the overall magnetic field of the Earth. All right, so because what's going on there is it's made mostly of iron and nickel. Iron and nickel are metals, and metals like to they usually have electrons that are free to move around. Right, and so this outer liquid core is moving at a different rate than the surface of the Earth, and that difference in movement between the the spinning liquid core and the spinning solid I mean, even if there's ocean there, right? It's you consider that solid. For the purposes of the magnetic field, you can consider that solid. Uh, that difference in rotation speed causes the Earth's magnetic field. Right? That they call, it's also known as in physics, it's called the dynamo effect. All right. So anyhow, that is. So here's the Earth, just kind of a cutout of the Earth. We have, of course, let me go from the inside out. Okay, so in the innermost part of the Earth, of course, is a solid iron and nickel core, as I mentioned before. Surrounding that, there is a liquid iron and nickel core. So there's two cores, and around the liquid outer core, the liquid core, is what's called the mantle. And this is kind of, I mean, it's a solid material, but it's almost like almost like a plastic that can I mean, it's rock that is under tremendous pressure, but it can kind of move around, right? It does move around, and the reason it's moving around is because the inner core, this solid core, is really hot. We'll get into why it's so hot in just a little bit. In fact, it's so hot that's why there's an outer there's a liquid outer core, right? That heat causes the iron and nickel a certain distance away to turn into liquid instead of being solid. It's solid at the center because of it's so much pressure. I mean, you got this incredible amount of mass that is the Earth. Remember, gravity is pushing towards the center of the Earth constantly. Gravity's always there, pushing towards the center, and that causes the core, the iron nickel, the center of the Earth, to be solid. There's a solid core, and then there's a liquid core because it's there's so much heat and you get far enough away from the center, and that turns into a liquid. All right, and then it turns into this kind of almost like it's not plastic. Okay, don't think it's rock. The mantle is just rock. That's where you find things like granite and stuff like that. Well, the granite's actually much closer to the crust, but the mantle is actually made of material called olivine. It's generally like kind of a greenish color, just to let you know. And then on top of the mantle is what's called the crust. And the crust is actually the thinnest part of the Earth. The mantle is the thickest part, and then comes the outer core and the inner core. And the crust is actually relatively thin, as it says here. It goes from 12 to about less than 50 miles, right? So we've actually dug into the mantle. I'm sorry, never. Sorry about that. Remember, the crust is 12 to a little more than 40 miles, and we've dug down a little more than 7 miles. So we've never even gotten into the mantle of the Earth. All right. Of course, volcanoes have, but that's a different story altogether. All right, so I'm starting to run out of time with this particular video. Let's see, the layers of the Earth. All right, so then the next one, I'm going to start talking about what's called differentiation. All right, so this basically is more dense material ends up at the center, and less dense ends up at the surface. All right, so that in fact that's what we find on the Earth. All right, the densest stuff is right there towards the core, and the least dense is at the surface.